This morning we're going to be looking at enthalpy changes. Enthalpy is a specific chemistry word and it doesn't mean the same as energy. People sometimes think it means the same as energy. It doesn't. It means heat energy. Okay? And we're going to be looking at the enthalpy changes involved in reactions. Now you're familiar with this from GCSE in terms of exo and endothermic. Okay? And we're going to be applying a bit more chemistry to it. So to begin with, you've got to be able to balance equations. This topic's not going to make much sense if you can't. And you've got to be able to use your balanced equations, sort of simple maths and so on. So, let's start with the first law of thermodynamics. Thermodynamics literally just means change in energy, okay, of a system. So, energy can neither be created nor destroyed, but it can be converted from one form to another. Okay? Energy cannot be created or destroyed. In chemical reactions, you've got some form of energy change, can be very obvious, e.g. energy is given out, or energy is absorbed. And those you're familiar with for several years now. And you know that things burning is giving out energy. That energy was stored in the chemicals, it's been released when it burns. Respiration is another exothermic process. Okay? And by respiration, I don't obviously mean breathing, I mean the conversion of glucose into carbon dioxide and water when reacting with oxygen. It's what gives your muscles energy, and the moment your cells stop doing that, they die. Endothermic reactions, photosynthesis requires light to happen, and classic example, thermal decomposition of calcium carbonate. That's what the rugby cement tower does. Okay, it heats up calcium carbonate, gives off the carbon dioxide, and you're left with calcium oxide. Thermal decomposition reaction, endothermic reaction. So, enthalpy, a measure of the heat content of a substance at a constant pressure. You cannot measure the actual enthalpy of a substance. You can, however, measure the enthalpy change. And this is written with the symbol delta H. Okay? Literally just meaning change in heat. First important equation for the day. Enthalpy change is the enthalpy of the products minus the enthalpy of the reactants. Okay? So the change in enthalpy, delta H, is the enthalpy of products minus the enthalpy of reactants. And we'll explain this in a bit more detail now. You should be familiar with this sort of diagram from GCSE. Okay? Just quick show of hands, how many of you have never seen one of these before?
Not I can recall.
Okay, it's about 2/3 of you. Alright, hands down. What we've got here is enthalpy on the y-axis. Okay? Effectively, a measure of energy. And what we have along here is basically a timeline. So to begin with, I have here my reactants, and they've got some energy. You happy with that? My reactants, they've got some energy, they've got some enthalpy. Put a bit more energy in, and then they can react together and give their energy out. Okay? It's not ringing any bells at all. You really should have seen this at GCSE. Thank you very much. I think I did show you this at GCSE. It doesn't get examined at GCSE anymore, but it is the sort of thing you should be familiar with. What we're saying is, we've got some reactants, we give them a bit more energy, and we get some products. Yes? This energy that's got to be put in to begin with, this is the activation energy. Okay? Energy goes in, and then lots of energy comes out. Make sense? And the difference between the amount they had to begin with and the amount they had at the end, that's the enthalpy change of reaction. Is that making sense?
Yeah.
Yep? So we put some energy in, that's the activation energy, and then, in this case, we get some energy out. The products have got less enthalpy than the reactants. Make sense? Products have got less enthalpy than the reactants. So overall, delta H is negative for an exothermic reaction. These guys had quite a bit of enthalpy, We've put in a bit of energy, lots of enthalpy has come out. The reaction is exothermic, and this difference here is negative. All exothermic reactions have a negative delta H. Okay? And what that really means is the system has given out energy. Okay? If you think of a match, right, you burn the match, you're left with the ash at the end, but the match has given out energy to the environment. I know it's taken in oxygen and so on, okay, but the product, okay, which is the ash and the carbon dioxide and the water, has got less energy than the match and the oxygen had to begin with. Does this make sense? Yeah? Sure? Okay. If we were to look at an endothermic reaction, it looks a bit like this. You have to put in loads of energy, which is your activation energy, and then your products end up with more energy than the reactants. If I start with calcium carbonate, and I give it lots and lots of energy, and I end up with calcium oxide, okay, will react exothermically with things like water and carbon dioxide. Whereas calcium carbonate doesn't react with water. Okay? So this is where we've put in a substantial amount of energy. The reaction's endothermic, and delta H is positive. All good? So, standard enthalpy changes. These are a gift of a question, and you will probably get one in Module 2. You need to know some standard definitions for enthalpy changes. And these take place at standard conditions, which is pressure of 100 kilopascals, or 101 kilopascals to be more precise, which is 1 atmosphere. Okay? Standard conditions, an atmosphere of pressure. Okay? Unless we need to, we don't do chemical reactions under reduced pressure or increased pressure. So we do them on standard conditions, which is atmospheric pressure. Stated temperature, 298K. Bit of a random number, until you realise it's 25 degrees C, i.e. a nice, pleasant day. Okay? So standard enthalpy changes take place in atmospheric conditions, nice room temperature. Make sense? Okay. The delta symbol I've covered before, the H literally stands for heat enthalpy, and all of a sudden we've got the London Underground side. This symbol here means standard conditions. So delta, H, standard, sometimes you see the number 298 as well. Technically, I don't think you need 298 if you've got that symbol there. Okay? But 298 is the temperature. So standard pressure, stated temperature, and we've got a nice little bit of symbolism here. So the change in heat enthalpy under standard pressure and at 298K. Happy with that? Yep. Pretty good. Let's now look at standard enthalpy of formation. This is a really, really important one. So, delta H, and that should be one of these little underground signs. Delta H standard F. Oh no! New letter. F for formation. Okay? So the change in heat enthalpy under standard conditions for formation. Is the enthalpy change when 1 mole of a compound is formed in its standard state from its elements in their standard states. Now that's probably going to be a 1-mark answer, and you need almost all those words. The enthalpy change of formation is when 1 mole of a compound is formed from its elements, okay, in their standard states. But the compound has got to be in its standard state, and it's got to be under standard conditions. So, forming carbon dioxide, which is a gas in its standard state, from carbon, which is a solid in its standard state, and oxygen, which is also a gas in its standard state, okay, that is the formation enthalpy of carbon dioxide. You happy with that? This is forming water. Notice liquid, standard state, from hydrogen and from oxygen. And finally, in this case, ethanol. You would never synthesize ethanol from graphite, but the formation energy of ethanol is starting with graphite, adding some oxygen, and then adding some hydrogen. Does that make sense? Yep? We all good? Happy? So, we're talking about 1 mole of product. Okay, it doesn't matter how many moles you have to start with. If I've got 6 hydrogen atoms there, I must need 3 moles of H2, because that's hydrogen in its standard state. Yeah? Importantly, really importantly, because this pops up very, very regularly, elements in their standard state have 0 enthalpy change of formation. I.e., if you think about it, to make oxygen gas, okay, to think about the delta HF for oxygen, you'd be forming it from oxygen. So you've not changed it. And if there's no change, there's no enthalpy change. And if there's no enthalpy change, it's got to be 0. Does that make sense? So the enthalpy change formation of elements is by definition 0. We normally take carbon to be graphite because you really wouldn't make ethanol out of diamond. Just to check, are we all happy with formation? Right. Now let's have a look at combustion. Combustion is very similar. Delta H standard C for combustion. It is the enthalpy change when 1 mole of a substance undergoes complete combustion under standard conditions. All reactants and products are in their standard state. So, formation is about making something. Combustion is about burning something in oxygen. So, look at this equation here. Does that look familiar? Scroll back one. This is the formation of carbon dioxide, which happens to be the same as the burning of carbon. Okay? Burning of hydrogen to make water is the same as forming water. But then, ethanol reacts with oxygen to form carbon dioxide and water. Okay? So it's starting with 1 mole and burning it, whereas the previous definitions were about making 1 mole. You see the difference I'm drawing? Okay? One's about what you start with, the other's about what you finish with. Combustion is about what you start with, formation is about what you finish with. So, you only have 1 mole on the left-hand side. You can use halves for oxygen if you need to. That's no problem, because you're just saying burn it in enough oxygen to fully react it. And there we go. And that's combustion. Nice and straightforward. Enthalpy of neutralization, we're not going to cover that. Pops up in module 4. It's just the enthalpy change when you form 1 mole of water. We're going to talk quickly about bond dissociation energy. This enthalpy change here is going from Cl2 to 2Cl. Happy with that? It's going from gaseous chlorine molecules to gaseous chlorine radicals. The thing is, and then we've got oxygen to hydrogen here, and so on. An important point to note is when you quoted values, you're not quoted values for that specific molecule. You quoted values based on average values. So, something like a C to H bond, they will quote an average value from ethanol, methanol, methane, ethane, propane, and so on. Lots of different values get averaged to give you one value of C to H. Wake up. Okay? The smaller the bond enthalpy, the weaker the bonds, the easier to break. Okay? Smaller the bond enthalpy, the weaker bond, easier to break. And here are lots and lots of mean values. So this one here, this will have been taken from ethene, okay, from propene, and so on. There are lots of different molecules that have got double bonds. It has been calculated and then averaged across those molecules. And as you can see, as you go from single bond to double bond to triple bond, the values increase because the bonds get stronger. Okay? Carbon triple bond you get in a molecule called ethine, otherwise known as ethylene, okay? Otherwise known as acetylene. Very good. Okay? Right. Hess's law. You might well get Module 2 paper, state Hess's law. You've got to think, brilliant, Hess's law, definition. The enthalpy change is independent of the path taken. I.e., as long as your starting point and your finishing point are the same, the overall enthalpy change is the same regardless of how you get there. Does that make sense? Yeah? Sort of? Okay. Can we pause for a second, please?
Oh, wait a minute. Is that your phone? I'm going to zoom in.
This is an analogy and it has some flaws. But if I start off in Coventry and I want to travel to Rugby, there's several different ways of getting there. But I can go directly or I can go via Leamington. Okay, this is my very, very crude map of the West Midlands. Coventry, Rugby, Leamington. Okay? Now, if I set off from Coventry and I go to Leamington and I go up to Rugby, okay? The total distance away from Coventry has not changed. I know I've travelled further, I know it's taken me longer and so on. What I'm getting at is Coventry and Rugby are a fixed distance apart. And it doesn't matter how I travel between the two, they remain a fixed distance apart. Does that make sense? Okay? Obviously it's more involved, okay? You know, I can go down the A46 and then sort of up the, whatever it is, the 452, okay? Or I can just go all the way down the A45. The point I'm trying to make is, the distance between these two, okay, is not dependent on the route taken. Does that make sense? The absolute difference between the two. In just the same way, and if we can pan back and so on. In just the same way, if I have reactants A, products B, happy with that? And I have some intermediates here, X and Y, the total energy change from A to B is the same whether I do the reaction directly, which in this case is delta HR, happy with that? Or I turn A into X, X into Y, and Y into B. It's a bit more convoluted, it takes a bit longer, it's a bit more effort, but the total energy change remains the same. So Hess's law is very simply, the enthalpy change is independent of the path taken, or the route taken. Got it? Good. So in this case, and this is where if you're doing vectors, if you've done vectors in maths, this becomes very, very easy indeed. It's just application of vectors. Delta HR is delta H1 plus delta H2 plus delta H3. Happy with that? Excellent. If, however, you wanted to know delta H2, I'm going to teach this one of two ways. Okay? First way is to think, well, delta H2 is going from there to there, right? And going from there to there is the same as going from there to there to there to there. Happy with that? So that again, going from there to there is the same as going from there to there to there to there. Did that make sense? Yeah. Which means that delta H2 is minus delta H1. Because you're going in the opposite direction of the arrow. Okay? So if delta H1 is going from there to there, then going from there to there is minus delta H1. plus delta HR. What's the next word? Minus delta H3. Good. Get it?
Yeah.
Going from there to there. It's the same as going from there to there to there to there, which is minus delta H1 plus delta HR minus delta H3. Okay? There are two ways of doing this. One is you can write out an expression where it's all just added up. So that one equals that one, and that one added together, and then rearrange it. The other way is to use the vectors. It's saying from there to there is the same as minus that, plus that, minus that. Got it? Okay. What we now have to do is apply Hess's law to this formation business that we talked about earlier. So, if Hess's law states that the enthalpy change is independent of the route taken, it means we can work out an enthalpy change, okay, as a theoretical value from other given values. We're not going to worry about lattice enthalpy, that's module 4. So we can measure the enthalpy change of a reaction from bond enthalpy. We can measure the enthalpy change of a reaction from delta HC or delta HF. If we know these, we can work out the enthalpy change for another reaction that we don't know directly. Does that make sense? Yeah. So, I'm going to skip that. We can skip forward to this one, please. No. This is what I want. Sorry, this page here. This is your classic Hess cycle. If we have all our elements here, okay, and here we have delta HF for elements going to reactants. Does that make sense? So whatever my reactants are, and I can look up my delta HF values. You get data tables, okay, that quote these delta HF values. So I can find out the formation enthalpies of my reactants. I can find out the formation enthalpies of my products. Okay, these will be given to you, and you can use them to work out the enthalpy change for a reaction. Does that make sense? So, I personally don't draw diagrams like this. I find this sort of diagram much more simple. Okay? If I wanted to have an expression for delta HR, it would be this one here. The sum of the delta HFs of the products minus the sum of the delta HFs of reactants. Does that make sense? We go back to this one here. I'm saying that is equal to minus that plus that. Got it? That is minus delta HF for reactants plus delta HF for products, which is this equation. I have to say I have never ever in my life bothered to remember this equation. Okay? Because I'm so familiar with the Hess cycle and so on. I have got to the stage where I do now know this one by heart. Okay, but that's only because I've come across it in my teaching notes enough times. Okay? When I was a sixth former, I never actually bothered learning that because I could do my Hess cycles. If we think for a minute about burning, we can do exactly the same thing. If we know the combustion enthalpies of the reactors and the combustion enthalpies of the products, we can again work out the delta H for the reaction. Make sense? Now, you'll see this in lots of different diagrammatic forms, lots of different ways in textbooks. Probably just because it's the way I was taught it, I always put elements down at the bottom and do delta HFs going up. Okay? I would then, for combustion cycles, I would actually put the oxidation products above, and I'd have the reactants going up to the oxidation products and the products going up to the oxidation products. But that's just my way of drawing it. Okay? Elements underneath, combustion products above. But either way is fine. You can get the question, draw a Hess cycle for this. Okay? And you are expected to come up with a triangle. Okay? And so on. Again, never ever bothered learning that equation, but you can see that this equation here comes from that there. So going from reactants to products is delta HC of reactants minus delta HC of products. Got it? And the reason that I've never bothered learning them is that they're the wrong way round from the formation one, and I just get confused and so on. So I just draw my little Hess cycle and get the right answer. So, sample calculation. We are going to, you've been given some standard enthalpy of formations, and we're going to try and work out, standard enthalpies of combustion of carbon, hydrogen, and methane, and we're going to try and work out the formation energy of methane. Got it? Yep. So, delta H equals the sum of the combustion products of reactants minus the sum of the combustion products, minus the sum of the combustion of the products. That's what I was going for. And put it all in. So, reactants, 1 times delta HC of C, plus, where's this 2 come from? 2 hydrogens, 2 hydrogen molecules. So we have to combust 2 moles of it. Okay, minus 1 lot of CH4, and we get the answer of minus 76 kilojoules per mole. You're going to have a lot of practice at doing this, but in theory, does that make sense? Yep. Measuring enthalpy changes. How are we doing for time? Got about 5 minutes left in this session. Should be able to finish this bit. You can measure enthalpy changes usually by heating or cooling water. And to do that, you need a new equation. Q equals mc delta T, where Q is heat energy, M is the mass, C is the specific heat capacity, which of water is 4.18, and you don't have to remember that, you get given that. Q equals mc times delta T. Basically, the change in enthalpy is the mass times the specific heat capacity times the change in temperature of water. Get it? Okay. Example. When you burn 0.18 grams of hexane, it raised the temperature of 100 grams of water from 22 to 47 degrees. Calculate its enthalpy of combustion. Well, heat absorbed by the water is 0.1 times 4.8 times 25. Do we need to convert these into Kelvin? No, because there's a temperature difference, and temperature difference in Kelvin is the same as in degrees C. So, chuck all of that in. The moles of hexane was 0.00209. Therefore, the enthalpy change per mole is the number of kilojoules divided by the number of moles is 5,000 kilojoules per mole. Okay? Which is why it's a good fuel. Right. This takes a little bit of explaining. The group that I have 6 periods a week did this last week. The rest of you do it next term. If you were to measure this in a lab, particularly with 2 solutions you mix together, you do it in a polystyrene cup to keep the heat in. Okay? And what you do is you take the temperature of your solution. There it is. Okay, so this is like copper sulfate with iron powder going in. And I'm measuring the solution, and measuring the solution every 30 seconds, the temperature's not changing, yawn, 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 yawn. At about 3 minutes, I chuck in my other reactant. The temperature goes right up. And it goes right up, and then it starts cooling down. I'm carrying on measuring, and at this point, the pupils are going, this is the worst experiment in the world, I'm bored, I'm bored, I'm bored. Wasn't that bad. No, it wasn't. So, we've measured the temperature of a solution, right? We didn't measure it at 3 minutes, because at 3 minutes exactly we were chucking in the other chemical. What we then have to do is extrapolate to find the actual temperature change. So these points here, we can extrapolate along there. That's no problem. These points here, we can extrapolate like that. And we can work out the temperature change at 3 minutes. Got it?
Wow.
So by extrapolating what the temperature would have been at 3 minutes, had it just stayed the same, which it was going to, and extrapolating back to what the temperature would have been at 3 minutes if the reaction had fully reacted all at once. Make sense? Because the reaction's a bit slow, doesn't all react at once, so it carries on heating up. We get that change in temperature. Okay, that's one of your PSA practicals. My group did it last Friday. Everybody else will do it next term. You're going to plot one of those graphs, and that's how you do it. Example calculation, blah, 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 blah. We're not going to do that, and that's the end of this session. Can you pause, please?